made in one piece. But through the ages, armor and other equipment became more complicated, and various methods of joining metals were developed. Riveting is one of these. Another early method of joining metals was by welding, as, for example, when a blacksmith joined two white-hot pieces with his hammer blows. More recently, gas welding and electric arc welding have come into common use to join parts which do not have to be disassembled. The third method, the use of screw threads, dates back for centuries. Through the years, screw threads for fastening metal parts attained wide use, and today this practice is one of the most versatile and precise in industry. Truly, the use of screw threads is the key to modern manufacturing methods where disassembly, interchangeability, precision, and freedom from distortion are paramount. Because screw threads can be cut accurately by modern tapping methods, screws and other parts made on other machines by other manufacturers are completely interchangeable. With properly designed and accurately made taps, close tolerances can be maintained for unlimited interchangeability and extreme precision. And many of the complex problems of 20th century production have been solved because taps may be used to cut screw threads in any of the great variety of materials needed by industry. To see how screw threads are cut, let's watch a thread being cut on a lathe with a threading tool bit in a boring bar. Normally, this requires many passes. To illustrate another possibility, let's use a series of tool bits, chamfered so that each takes a slightly deeper cut. The result is a thread in fewer passes than with the single tool bit. Basically, the tap used in modern internal thread cutting is like a series of tool bits on a single shaft, the shaft representing one land of a tap. To get a better understanding of what a tap is, let's first watch one develop from a blank. First, centers are cut in the tap blank. The line connecting these centers is the axis. The shank end is usually squared for driving purposes. Grooves parallel to the axis are called the flutes. The part of the tap between flutes is the land. The teeth of the tap are formed by cutting or grinding a screw thread on the lands. The part of the tooth that enters the work first is called the cutting face. The part that trails is the heel. The end of the tap is eccentrically ground on a taper called the chamfer. We now have a complete tap. Let's see the dimensions that are used in specifying taps. These include the overall length, the length of thread, the diameter and length of shank, size and length of square, chamfer, and point diameter. The major diameter is the outside diameter of the full threads. The minor diameter is the diameter at the base of the threads. The pitch diameter is the diameter at the point where the width of the tooth is the same as the width of the space between teeth. The pitch is the distance from a point on the thread to the corresponding point on the next thread measured parallel to the axis. The crest is the top of the thread. The root is the bottom surface joining the sides of adjacent teeth. The helix angle is the angle made by the tangent to the helix of the thread at the pitch diameter with a plane perpendicular to the tap axis. The tap tooth may have relief called thread relief or radial relief. This keeps the tooth at the heel of the land from rubbing on the work. If the cutting face is flat and parallel to a line through the tap axis, the face is said to be radial. If the face is flat but not parallel to a line through the axis, the face has rake. The rake angle is the angle between the face and a line through the axis. Here the rake angle is positive, and here it is negative. If the face of the tooth is curved, it is said to have hook. With the overall nomenclature and dimensions of a tap in mind, let's see exactly what a tap does. As the rotating tap is brought into contact with the work, the first tooth on the chamfered portion enters the drilled hole and takes a light cut of the material. The second tooth is led into the work by the first tooth as it cuts its way through the material. The second tooth makes a slightly deeper cut. Each tooth cuts its way through the material in the same way. Following teeth take successively deeper cuts in the spiral groove until the tap enters the work to the full length of the chamfer. All of the other teeth normally on a tap will now follow through the same spiral groove as the first tooth of major diameter. But the teeth following the chamfer are not cutting teeth. There is actually a slight reduction in diameter of the teeth along the length of the tap. This is known as back taper. Yes, this tap will do essentially the same job as a complete tap if the head, spindle, chuck, tap, and drilled hole are held in perfect alignment. Here in cross-section of the hole just tapped, we see that the thread is accurate in every detail. Teeth back of the chamfer are used to guide and support the tap as it goes deeper into the work. And when the tap is withdrawn, by reversing its direction of rotation, these teeth assure a smooth withdrawal. More important yet, they permit the tap to be sharpened time after time and provide the flutes for chip removal. The action of all taps is essentially the same, although the variety of taps available is almost endless. Let's look at some of the taps used most frequently for many different purposes. Because tapping was originally done by hand, the most commonly used taps were, and still are, called hand taps. There are three types: taper, plug, and bottoming. The taper tap has the longest chamfer, the bottoming tap the shortest. The plug tap is the most commonly used type. It is used for through holes or blind holes where depth of hole permits obtaining desired length of full thread. If, however, the full threads must run almost to the bottom of the hole, a bottoming tap, which has only a 1 to 1.5 thread chamfer, is used to go to the required depth. A bottoming tap makes it possible to have perfect threads all the way down. The gun tap, a very strong and free-cutting tap, was developed to minimize tap breakage. This high-production tap shears off the chips and shoots them ahead of the tap, hence its name, gun tap. This tap can be used in either through holes or blind holes where there is plenty of untapped space to accumulate chips. Because the chips are shot out ahead of the tap, the flutes are not needed for chip removal. The shallower flutes result in a stronger tap. To cut certain thread forms or to thread very tough materials, a series of taps may be used. These taps come in sets of 2, 3, 4, or more. Each tap cuts a progressively deeper thread. The pilot centralizes and guides the cutting. The final tap in the series produces the finished thread. Most tapping problems can be solved with standard taps. These tools have been provided with a flute and cutting face design, which experience has proven to be best adapted for most tapping requirements. For example, here a standard stock tap is cutting satisfactorily over a rather wide range of grades of steel. While standard stock taps may be right for many materials, they will not give best results in all materials. Since the material to be worked is so important in the selection of the best tap for the job, let's look at some of the differences. Naturally, we can't go inside to see the action of the tap at work, so we'll watch the action of a lathe tool bit ground to the same specifications as the cutting face of the tap. Here in special photography, which shows the action 100 times slower than normal speed, we see the tool bit cutting a piece of cast iron, a very brittle metal. The bit has no hook and very little rake. See how it shears the metal. For brittle metals, therefore, a tap will have a cutting face with no hook and very little rake. On the other hand, metals that are tough, such as cast steel, require a tool bit with a moderate hook or rake. The same is true of a tap for tough metals. Ductile metals generally require tool bits with a much greater amount of hook or rake. Again, we see the cutting tool at work at 100 times slower than normal speed. For ductile metals, the tap will also have a distinct hook or rake. This is also true of aluminum, which requires additional hook or rake for best results. So the tap that is used in this material will also have a distinct rake or hook, or, if the aluminum part has a through hole, a standard stock gun tap may be satisfactory. While the material will determine the amount of rake or hook to use, very abrasive materials which wear taps rapidly call for something additional. If taps used in zinc die castings, bakelite, and similar materials are slightly oversized in the threads, tap life will be increased without exceeding tapped hole tolerances. Just as there is no one best hook or rake for all jobs, neither is there one best surface treatment for all taps. The best surface treatment generally depends on the type of material being tapped. Precision-controlled normal heat treatment gives the best surface treatment for the majority of tapping applications. However, special surface treatments for special cases are available. Chromium plating is one of the available surface treatments. Where friction is a problem, chromium plating improves performance in many cases. Another type of surface treatment applied to taps for use in abrasive materials is the maxi surface treatment. A fourth type of treatment called the steam oxide surface treatment, is notable for its friction-reducing properties. We have seen how differences in materials will affect the choice of a tap for a given job. Now let's see the effects of improper tap selection. Improper selection is, of course, one of the most common causes of tapping troubles. For example, a plug tap may have been selected for tapping a hole deeper than twice its diameter when a gun tap would do a much better job. Here is another example where a cut thread tap is being used. The threads are all right for a cut thread tap, but the designer asked for tolerances which cannot be maintained by this type tap. A ground thread tap like this one should have been selected for this job. Ground thread taps are threaded after hardening and consequently have greater accuracy. Another common tapping trouble is found in faulty machine conditions. Any misalignment of the tap with the drilled hole will result in bell-mouthed holes or a broken tap. Gauging the hole demonstrates the results. No screw can be made to fit that hole properly. Here is a tap correctly selected for cutting the material and with proper surface treatment properly set up on a good machine. It is operating at a tremendous rate, temporarily that is, because the machine was running too fast for conditions. Let's check this big job now. Everything seems under control. Alignment is perfect all the way from spindle to drilled hole. Tap is correct for the material, and so is the speed. As you can see, there's only one thing wrong. The coolant isn't getting to the cutting point. Look at the tap smoke. Another common tapping trouble is improper hole size. The hole size should be such that the tap teeth cut to about 75% of their basic thread depth. If the hole is too small, the tap might cut to its full thread depth with excessive torque placed on the tap. The tap may become loaded with chips, causing clogging of the flutes. Teeth may break off, and eventually the tap will break. Tapping troubles also include human errors. The operator brings the tap into contact with the work. The tap engages, but he does not allow it to follow its own lead. He's in a hurry and tries to force it. This thread is the work of the strong arm operator. A sloppy, oversized thread is the result. Compare it with this good thread, made on the same setup. Accidents are another cause of tap trouble. Have you ever seen this happen? Careless handling. That drop did more than chip the floor. Or have you ever seen a tap dropped out of the chuck? This kind of carelessness costs industry thousands of dollars every year. Being careful pays. There comes a time when even a properly used tap must be resharpened. This means regrinding a surface following the contour of the relief on the chamfered teeth or the cutting face on the land. However, it is easy to resharpen a tap on machines designed for this purpose. So far, we have considered what a tap is and some of the problems involved in getting a good internal screw thread. We have also seen that interchangeability of parts is the key to modern mass production. But a tapped hole is only one half of any thread assembly. External threads or screws are the other half. Since the screws used in mass production themselves are not made on the same machines as the nuts they mate with, the problem of interchangeability may reasonably be said to start here. Gauging determines whether or not the threads have been held within the allowable tolerances to assure interchangeability. In good gauging technique, the go plug gauge should go through the entire thread length, and under certain conditions, The not-go, or high-limit gauge, is permitted to enter the full length of engagement snugly. Normally, the not-go, or high-limit gauge, should only enter the work about 1.5 turns. Both gauges should always be used. The limits established by the designer will determine the gauge required and also have an important bearing on the cost of the part to be manufactured. The quality of the gauges must also be considered, because a poor gauge that rejects good product is an expensive tool. One of the most important factors in production tapping is availability. A large stock of standard taps is maintained in all standard sizes in factory sales offices and industrial distributors in every industrial center of America. In general, taps are divided into two groups: regular or catalog-listed taps and special taps. The use of regular taps is recommended wherever possible because special taps require special production handling. If, however, the special tap can be specified to regular tap dimensions, hardened tap blanks can be put through the finishing operations relatively quickly. First, the body and shank are ground to size. Then the blanks go to the automatic thread grinding machines, where the specified threads are formed. Next, they go to the automatic chamfering machines. After chamfering, the taps are carefully inspected. Only when each has passed the rigid inspection is it ready to receive its final OK, the trademark that guarantees highest standards of materials and workmanship. But of course, there are times when a very special tap is the only solution to a difficult machining problem. Even so, increased tap costs are more than offset by the increased production they make possible. For example, a pump manufacturer wanted a tool which would tap 3 concentric holes in one operation. This special tandem tap was designed to cut 1" 12, 1 1/8" 12, and 1 3/4" 11½ threads in one pass. This tap more than made up for its higher initial cost in higher production on the job. But whether the tap is standard or special, the men who design and produce them are constantly searching for better ways of improving performance and manufacturing methods. Research in better cutting methods, for example, developed the need for this electronically operated torque tester. With this machine, the amount of torque required is recorded for a plug tap and a gun tap of the same size as they cut through a steel plate. The torque required for a gun tap is considerably less than for a plug tap. Special research is carried on in the field of surface finish, too, a most important factor in tap and gauge efficiency. And in the field of metallurgy, continuous chemical and physical analysis are integral parts of the research program. As a result of this continuing research, many special machines for the manufacture of taps also have been developed. Precision indexing of flute milling, mechanically controlled flute grinding, the development of the high-pressure lube and coolant system on these automatic thread grinders, each the outgrowth of a research project, have resulted in greater tap life. All of the advantages are passed along to the consumer in the form of better tools and lower cost per tapped hole. To meet the production demands of a growing industrial world community, more and better thread-generating tools are being produced. Tools for use in the United States, faraway Australia, South America, the world over. Changeability of parts, the key to mass manufacture.